Welcome to Advanced Reverse Engineering. There's homework. The homework is to write this super complicated hello program that takes a number of times and a name, and then just prints that name that number of times. The thing I want to emphasize is if you find an error, start your error message with the word error so that my automated checker will pick that up. Command line arguments are going to come to you in EDI, which is where you'll find argc, and RSI, which is where you'll find RV. This should make sense given the calling convention. I'm going to build your program with that line down there below. Pay attention to registers. Pay attention to registers. Pay attention to registers. If you want to use a register, be aware that somebody else might want to use that register as well. To prevent conflicts, we have a calling convention. Honor the calling convention. Let's talk about tools, and in particular, let's talk about Ghidra. So, Ghidra is an NSA-developed reverse engineering tool. It's a combination of a lot of different tools, and it's a platform for developing even more tools. So on the service level, highest level, Ghidra understands file formats and it knows how to disassemble binary content. Highest level, you can think of Ghidra as a disassembler, an interactive disassembler like IDA Pro. But Ghidra is actually quite a bit more than that. It does decompilation, it does some semantic analysis of the program. Very powerful tool. You can install it. In order to install Ghidra, you unfortunately have to also install the Java Development Kit. At present, the version you want is JDK 17. You can install that on Ubuntu with just sudo apt install openjdk 17 JDK. Once you've installed it, you can run java-version to be sure that the system is seeing the correct version of Java. If it is, great, you're ready to go. What you need to do then is go to the address on the screen there and download the latest Ghidra release. At the time of these slides, that's 10.1.2. And you can download that and you're good to go. You can build it from source if you'd like to try to do that. That's fine. But in general, it's easier to just go ahead and grab the pre-built version. Installing is pretty simple. The way I tend to install it is I make a little opt directory under my home area, and then I decompress the Ghidra zip file, which is how it comes to you, into that directory, and I make a symbolic link so that I get the correct version. There are reasons that you might want to use more than one version, but if you just want the latest version, that's nice too, because it reduces the path to just opt Ghidra. You will probably want the logo. The version we have here has a broken logo. The slide tells you how to fix that, and it also shows you how to run it. There's a script that starts it. You'll find that in opt Ghidra. If you've created the symlink, Ghidra run. You can just run that script and it will go. You can create a desktop launcher. If you take the text that you see over on the right and you drop that into a Ghidra.desktop file, and you put that file in .local share applications, then GNOME will figure that out and you'll have a nice desktop launcher for Ghidra. When you start Ghidra, you'll come into this dialog right here. This shows you the projects that you have active. In this case, there are no projects active at this time. Now, you can have two different kinds of projects. You can have projects that are shared with others to collaborate, and you can have projects that aren't shared. And We'll see that in just a moment. So a Ghidra project can contain multiple files, just like anything on your system can be composed of multiple files, right? An executable is an executable, that's fine, but it may have libraries, it may have other executables it uses, it may have data files it uses. All of those can be put into the Ghidra project. Just import them in. So the basic idea is you want to make a new project, so you go to File, New, and like I said, there are two kinds of projects. Shared projects are intended for collaboration and they require a server. If you want to know all about that, there's a link there that will show you how to get that set up and going. But if you just create a simple non-shared project, you'll be good to go pretty quickly. You'll then import the files you want. You can import them with the import option from the file menu, or you can just press I to get the import dialog. If you're loading external libraries, you may want to let Ghidra go ahead and load those, or loading something that links to external libraries, excuse me, you may want to let Ghidra go ahead and load those as well. You can get some errors. Code that I have created and analyzed with it sometimes gets some funny Ghidra errors. strip, which is a very aggressive form of the strip binary that really rips out everything you can think of in your file, can result in a little set of warnings. You can ignore those. Ghidra is going to do its best to figure out what's in the file. Once you've got it open, you'll have a tool chest that will no longer be grayed out. It will become active. The code browser is the little Ghidra head. The debugger is the bug, and the version tracker is the little footprints. You can add other things to that. Once you have several versions of a program, you're going to want to be able to port analysis from one to another, right? So if you've got one version, let's say a piece of malware, and then you find a new version of that same type of malware, a lot of your analysis from the previous one may apply to the new one. There's a really cool tool to let you work with that in Ghidra. You create a new version session using this tool, and then Ghidra's correlator tool will help you move things over. There's a lot to say about that. I'm not going to say it here, I don't have time, but I've posted a YouTube video that seems to do a pretty good job of covering that. Once you're in the code browser, you'll see a number of things. The center of the screen is largely taken up by a disassembly. And you can see on this one, what we're looking at here is a bunch of data, right? We have DB, data bytes, DS, which is a data string, DW, data words, so on down the list, right? Instead of, you might think, well, what is this funny looking thing right here? Well, DDW, data double word, that's right, that's what that is. DQ, data quad word, sure. So there you go. Now, if there were some code in that space, we'd expect to see disassembly. And Ghidra does a best effort to figure out what is code and what is data. But as we know, that's not a clear distinction. So Ghidra can get it wrong. It can say some things are data when they're really code, or some things are code when they really should be data. And Ghidra can get it right and say something is code, but it might also be data, or something is data, but it might also be code, and there are ways to deal with that. As you move around in the code, you might double-click something in the code display, like the name of a routine, and it will jump you there. You might wonder how to get back to where you were. It's like a web browser. It has forward and back arrows for navigation up at the top of the screen, and you can use those. You can set bookmarks, just like with the browser. Set bookmarks by typing Control D, and that will add a bookmark. the sections that Ghidra recognizes in your file show up on the left-hand side in the panel, and you should recognize some of these, right? You should recognize BSS, data, there's GOT and GOT PLT, etc. If we scroll down, we'd find text and all the other usual sections. Clicking on those changes your display in the center to focus on the content of that section. Imports are shown. Exports are shown. What are imports? Imports are the externs that you reference. What are exports? Exports are the globals that you define. Functions. Ghidra does a best effort to figure out what is a function in your program. And you could imagine how you might do that, right? You might look for the usual function preamble. Right? I'm pushing RBP, I'm moving RSP into RBP, or I'm calling enter, or I'm doing any number of other things that look like the start of a function. And so Ghidra might say, this looks like a function, here you go. And it tries to then decode additional information from the file, like to demangle C++ names, and so on. So there's a filter down at the bottom if you want to look for something. You could look for main, you could look for start, you can see if you can find those things. And if there's a symbol defined for them, you might be able to find them. Now, if your executable has been stripped, well, those labels are probably gone and you won't find them. You'll have to use some other method. The main disassembly window, in this case, we're looking at an ELF header. And so you can see the usual ELF stuff, 7F, followed by the characters ELF, followed by the different information that goes into the ELF header. If you'd like to comment something that's in that window, push semicolon. And just like you do the semicolon to comment in NASM, that will bring up a comment editor. Now, instead of just typing the comment right there in line, it'll actually bring up a little editor so that you can create a more complex comment associated with that. Lots of things are links. If you want to know something to link, go hover over it. For example, here we see the entry point listed in the header for the ELF file. You can double click that, and in this case it will then jump you to where it thinks the entry point is in the disassembly. You can use the back button to then return to where you were previously. There's a decompiler. Decompilation is a whole topic, and we'll spend a little bit of time looking at the way in which this stuff works. In particular, we'll see how Ghidra is able to do some of the things it does in terms of decompilation, and we'll see how to do some of that ourselves. But Ghidra here makes a best effort to do some decompilation, and it shouldn't look too unusual to you. You should recognize libc start main. That's what we've been looking at when we start a C program. Now, it might look a little odd that there's a do while true in there. That's okay. Remember, libc start main calls into our main function and runs it. Okay, and that's what it's going to do. At the end, we're going to call, we're going to call exit, or else we're going to return to the C runtime, and it's going to call exit. So we're never going to come back here. So that infinite loop is really just for show. And Ghidra is going to do a best effort at decompilation. It's going to look ugly, but there are things that you can do to clean it up. You can go ahead and click on variables, on function names, etc., and you can change them. You can edit them. And that gets propagated through so that then you can have more symbolic names for different pieces and record information as you go. Ghidra produces a flow graph. You're going to be producing a flow graph later on, but it shows you the flow structure of your program. And again, it does a best effort. It's not going to be perfect and beautiful. And in particular on the right hand side, you can see it got a little bit, it's a little messy over here. This line goes over here and down, and it sort of interacts with this piece, but not really, right? This is not meant to connect with any of these little boxes. So it can be a little messy, can be a little ugly sometimes, but again, it's doing a best effort, and it's actually a fairly useful way to look at the flow of fairly sophisticated pieces of code. We've already looked at how we can take a look at flow graphs and learn some stuff from them. In particular, look at this. This little piece looks very much like an if-then right here. And you can see we jump over here, we jump over here. All of these take us to this little place, and we sort of go down this path. And you can click on these and see where you are over here, and vice versa. It's a pretty nice way to look at it. So Ghidra supports debugging using installed debuggers. Debugging is a complicated process in any world for anything. There's always going to be a lot of provisos and things associated with debugging. So we're not going to try to go into all of that, but I will give you enough maybe to get you started. To debug a file, right-click the file and choose Open with Debugger, or you can just drag the file up and drop it on the debugger icon, and you're good to go. So the debugging session is started with the little bug icon at the top of the window. You can debug remotely, should you wish to do that, via VM, etc. And there's a target icon that lets you set that up. I actually found it not terribly hard to make that work, and I think that you can manage that as well. Debugging controls are right there at the top of the little objects display. You may have to look for them a little bit. Every time I bring this up, for some reason, I don't know where to look for them, and it takes me a moment to get oriented and find them. They're the usual ones, right? Step over, step into, step out of, etc. All right. So with that out of the way, let's discuss the history of computer memory. Let's think about the evolution of memory in computers. And I mean short-term memory. I mean volatile memory, not persistent memory, but the stuff that you write to what we would think of as the memory in the computer. And we had this picture. Remember this picture where we have the CPU and memory as an associative array. There's an address bus, there are control lines, and then there's a bidirectional data bus to allow us to communicate. We read from memory with a fetch. We put an address on the address lines. We assert read. The memory controller goes and finds what we're looking for. It puts it on the data lines. The CPU is able to read that, and all is good. If you'd like to know how to build a computer memory basically from scratch, Ben Eater has a great video where he does precisely that. So he'll walk you through like the gate level version of building a flip-flop and then building a memory out of that, and then he'll do it on breadboard and demonstrate it. It's really cool. If you like that kind of thing, I recommend you watch it. If you don't worry about it. We're not going to try to build a computer out of breadboard in this class. There are many different ways that memory can be accessed. The most common many for very simple embedded systems, and for some older machines was just sort of direct access. Everything in memory had an address associated with it. There's an address bus, and some of those addresses could be memory. I'll say this again. Remember that everything in the computer is not necessarily used for what its ostensible purpose is. It is used for effect. And in particular, memory addresses are used for effect. A particular address could point to a spot in memory where I can store something. It could point to a piece of ROM where I can't change it, but I can read it. It could point to a device, so when I write to that, I'm actually writing to a register in a device somewhere, maybe modifying the operation of that device. Or I read from it. I could be reading from a register from a sensor, so I'm reading a sensed value out of it. Or there might be nothing there at all, and if I read from it, I might just get, stray garbage. So this is true for fairly simple processors. It's also true for the x86 when it's in real mode. There's no memory management in real mode. Protected memory access comes with protected mode. Okay? When you have this kind of a memory model, you seldom have a notion of allocation or deallocation. You just have addresses, and you have to decide where you want to store each thing. And you would build a memory map for your application so that you wouldn't run afoul of the other pieces of it, especially if you're trying to work in a team to build something. An example of the memory map is the Pac-Man memory map over on the right-hand side. Right? We have a set of addresses. There are different things at those addresses, and this shows some of the things that are stored at those addresses. If you want dynamic allocation, then you will have to keep track of the heap. You'll have to keep track of addresses and manage all that yourself. So there's also our friend, the Harvard architecture. And you remember the Harvard architecture separates, or tries to make a separation, between program memory and data memory. And an example of a chip using the Harvard architecture is the AVR. The AVR you might know as the chip that is in the Arduino. So the AVR has a modified Harvard architecture, and this is sort of an example of what it looks like on the right-hand side of this slide. You've got some flash memory, you have data memory, and you'll notice up at the top of that 32 general purpose registers. That's right, the register file is in memory and can be addressed in that way. And then there's the electrically erasable programmable read-only memory, EEPROM, which holds your program. So lots of stuff to talk about here. I'm not going to get into all of this stuff, but you can see the EEPROM, which holds your boot up stuff because it's persistent across boots. Flash, which holds some information. There's a boot section there. The data memory. These are all actually on the chip itself. So AVR is pretty neat. If you'd like to learn more about it, I got a link to AVR developer information. Harvard and von Neumann, we've talked about it before, but if you really want to deeper dive into it, there's a video that will do that for you.
The Harvard architect.
Yes, very lovely voice. So the direct access model works well if you have discipline, plan ahead, and are usually only running one process, right? You want processes trying to step on each other. If you only have a 16-bit address space, lots of processors only had a 16-bit address space. Some modern processors still just have a 16-bit address space. How do you deal with more than 64K, right? A 16-bit address space can address 64 kilobytes of memory, but not really anymore. So how do we deal with that? Well, we can deal with it using bank switching. You pick a special address and you write to it. Often it's an output port. That address is hardware mapped. It stores the value you write in a special register. It feeds that value to a decoder. The decoder feeds to the chip select inputs on different memory banks and lets you select a bank. What am I talking about? This sounds crazy. So imagine that location, let's pick one, location 4, address 4, actually points to a register that holds a byte, and it selects one of 256 other banks. Okay? Each one of those banks has, let's say, 32K associated with it. That's 128 times 32K. That's a lot of memory. And whatever number is present in there selects that bank. And that works. That's how a lot of this stuff was done. That's in fact how the Commodore 64 was able to have 64K of RAM while also having ROM and other stuff present. You could bank switch those out and get access to the RAM. That all sounded crazy. Let's go back and talk about that for just a bit more. Basically what happens is you gain some address lines by storing the top part of the address space in a register somewhere, and then you just use the low 16-bit lines as the usual address lines. Hope that makes sense. So here we have a case where we've got 2 additional address lines, and those 2 are used with a decoder to decode 4 different potential banks, right? Because 2 bits have 4 different possibilities, each one of which will select one of those output lines. That would be fed to the chip enable. Since only one is enabled at any given time, they're all connected to the address bus. They're all connected to the data bus. But only one of them is enabled at any given time based on what you've stored. And that's the one that you get. So memory becomes something that is starting to be a little bit decoupled from just the straight address lines, right? So we might use something like this. This is a transparent latch that also has a 4 to 16 line decoder. Great. I can set something into the latch that will choose which bank I'm now going to talk to. I'll talk to one of 16 different banks, and I can then use my 16 address lines to address 64K in each of those banks, right? And that gives me a lot of memory. And I have to keep track of, what have I put into the latch? I need to know that because that's sort of the top 4 bits of my address space. And I don't want to be trying to bank switch lots. I want to tend to run a program in a particular bank, and then maybe I swap to a different bank and I run a different program in that bank. So a particular 16-bit address in the program could refer to one of potentially 16 different bytes, depending upon which bank is in place. So memory's a little bit virtual, right? It's not exactly the way that it was in the flat model. It's beginning to get a little bit of separation between the address and memory. 16 banks of 64K would give us access to a full megabyte. That's great. Controlling bank switching can be a little bit fraught. Let's say that I'm running code in one of those banks and I want to switch. I have to figure out how to do that because the program counter, after I set a new value in that latch, it's going to be executing out of a different bank. And so sometimes what you would do is set aside a small chunk of each bank's memory to deal with bank switching, right? I would maybe put a resume address somewhere. I would then jump to this, which would switch the bank for me, and I would then go to that resume address and begin executing. It's a way to handle that. So that's complicated. That's using up some of my memory. Maybe what I could do is have another controller that managed some of this for me. I might call that a memory management unit. And the processor can use addresses, and the MMU is then responsible for handling all the details of latching stuff and managing stuff and multiple program counters and all of that. It'll deal with that for me. This pretty quickly leads us down the path to dynamic address translation. And in fact, very quickly, so you imagine these big machines begin to be put together in the late 50s into the 60s, and over the course of the 1960s we hit virtual addresses in about 1966. It does not take very long before we realize we have to have a way to manage this. And there's sort of the seminal paper in this. Program an addressing structure in a time-sharing environment. And you see, right there, section 5 is titled Paging. And you see at the bottom there, blocks, pages of code being mapped to storage sort of arbitrarily. You've decoupled the address from the actual storage. You've made the address virtual. And then something has to handle the mapping of these virtual pages to real memory, and that thing is the memory management unit. Its job is to translate virtual addresses from the CPU. CPU, all it knows is, I got an address. I want to put a byte at that address, or read a byte from that address. The MMU translates that into whatever the appropriate physical address is and handles that for you. And there are lots of advantages. One is memory protection. The MMU is like a tiny little computer inside your computer that can enforce some rules about memory. Right? You're not directly accessing memory anymore. You have this piece of logic between you and the memory, and so that piece of logic can control some things. It can say, you're not allowed to write to this memory, or you're not even allowed to read from this memory. And it can manage that sort of stuff for you. It helps solve the memory fragmentation problem. Imagine that you've got, you want a big chunk of memory, so you allocate a big chunk. And then you allocate a small chunk. And then you free that big chunk, but you allocate a bunch of small chunks. And you can imagine where those all are. And as you allocate the small chunks, you're getting closer to those previously allocated chunks, and the space that you have available is smaller and smaller. And you begin to get these fragments everywhere. And you'd love to put them all together so you can allocate a big chunk of memory. There's no good way to do that. With this kind of approach, you might allocate a page. And you might want 5 pages worth of memory. Fine, you can take them from wherever you want in physical memory, and then through virtual addresses make it look like they're all together. It deals with address translation, which means that different processes running on your machine can have the same address space. Right? I always want my program to start at let's say 1000 hex. I can do that. Each program can have its own virtual address space. And 1000 hex for these each of these different programs can be similar or different in physical memory, but they all virtually see the same thing. Caching is going to show up. It's going to provide for much faster memory access. Caching is already around, but the memory management unit allows you to make really clever use of caching. You can access memory larger than the processor's address space. I mean, you can imagine that each process has a 16-bit address space, but physical memory could be much larger, and each of them is now seeing their own little 16-bit address space virtual world, whereas the real memory is potentially a larger space. And you can do error detection. You can catch some bugs. We divide memory into pages, and the MMU keeps track of those pages for us. We use a page table to track permissions, and because all of this can be complicated, we use something called a TLB, or translation look-aside buffer, to help us do rapid address translation. We'll see that in just a moment. If you want to know all that stuff, here's a good video that will go through all of that in more detail with you.
Let's take a
We're
look
going to
at
hit it
an
at a
example
kind of
of-
high level next. So up there on the right hand side, you see an IBM System 360 in Michigan in 1969. And it had an MMU. At the bottom of the right hand side is the MMU from the Commodore 128. So external MMU systems existed that you could add to memory management. Not so much these days. These days, modern processors have memory management built into them. The x86 in particular is interesting. It has a lot of different operating modes, and it's actually Turing complete. And an example of that you can see playing out over on the right hand side of the slide. You see Conway's Game of Life being played. It's being played without executing any instructions on the processor. It's basically operating through memory faults. This is the memory management system by itself playing Conway's Game of Life. If you want to see how that works, I've got the link to the GitHub page up there. But memory management becomes very, very complicated. More recently, we have this notion of heterogeneous system architectures. We're moving to a world where we want a combination of CPUs and GPUs to do some work. And so over on the left-hand side, you can see I've got an application and I transfer some buffers to GPU. And so the CPU has to then help me copy that information over. Finally, it gets to the GPU and I can run the job, but then I've got to copy everything back, and so the CPU has to be involved in that. Over on the right-hand side, you can see where the HSA Foundation wants us to go. They want a much cleaner, at least conceptual, process for getting data from an application into and out of the GPU. So you need to understand the notion of virtual memory if you're going to write your own operating system. Okay? You need to understand how paging works. You need to think about physical versus virtual addresses. You need to think about permissions. All of those things if you're going to write your own operating system. If you're not, you still need to know a little bit about it, but not as deeply. Let's talk about memory management on Linux, since we're using Linux. So in Linux memory management, it looks like memory management in most operating systems because, again, you're using the same chips. And the chips enforce a lot of this within them, right? The Intel and the ARM, they have page tables and translation look-aside buffers and all the usual stuff. And so that's what you're going to see. So each process is going to have its own virtual memory map. It's going to have runtime structures like GOT and PLT. It's going to have executable code. It's going to have some data. It may have a heap. The heap is going to grow upward toward high memory. There could be some empty space there for it to grow into. Sometimes there's other stuff in there, like dynamic libraries get mapped into that space, right? They're loaded somewhere in physical memory, and that those physical addresses are then mapped into your address space. Because, again, we can virtualize the addresses and they can then appear. We follow that with stack, usually get higher memory, growing downward, and then that's often followed by hardware vectors and other stuff. So here's an example of a simplified Linux process memory. We don't use the very lowest bytes, we don't use the very lowest addresses. There may not be any bytes there at all. The very lowest addresses we don't use. We typically start around, about a third of the way up the 48-bit address space. So there we go. You can see all those 5s there. And then you'll typically have like the PLT, which we'll talk about, the text section, data, BSS, and the heap growing up, the stack growing down, and we don't use those highest addresses. And when I say don't use, I mean there's just literally nothing there. Is there a byte at address 0? Probably not. There could be a byte at physical address 0, but if I haven't mapped anything to address 0 in my virtual address space, there's no memory there. Keep that in mind. So the address space is virtual, no obvious direct relationship to physical memory. Don't think of an address as equaling a real byte. Right? An address might just be an address, and there might not be anything there. Okay? Virtual memory addresses don't exist unless allocated. Now, if we use all 48 bits of the available address space, we can address up to 2 to the 48 bytes, and that's 281 terabytes. Do you have 281 terabytes of memory in your computer? If you don't, then you don't have a byte associated with every address. Right? Some addresses simply don't exist in the world. Let's think a little bit about memory hardware. Now, I've been saying 48 bits. What do I mean? Well, I mean 48 bits. It may even be 40 bits. Virtual addresses are limited to 48 bits, and physical addresses are limited to 40 bits. Although on some newer processors like the one I'm doing this on right now, it's 48. That may surprise you, because you may think, oh, it's a 64-bit computer. You've been telling us that pointers are always 64 bits because memory addresses are 64 bits, and now you're telling me they're just 48 bits or maybe 40 bits? What is this? So you can go and see what your computer has. Cat proc info CPU. Oh, sorry, cat proc CPU info. Grep out address, and it will tell you the size of the different address buses. And it'll typically be 40 and 48. The x86 MMU is going to translate virtual addresses into physical addresses. And physical addresses, you can think of them as physical locations in DRAM, and that's fine. It's a perfectly fine way to think about it. But remember, DRAM has its own controllers and tables and so forth. There you go. Virtual addresses on the x86-64 are 48 bits. And registers, little pointers, are 64 bits. What happened to the top 16 bits? Right? Well, they're redundant. They hold copies of bit 47. And that's because the top 16 address lines literally don't exist. They're not there. They don't exist. You have 48 address lines. And so those top 16 are all just copies of the last one, which is line 47. And so if that last one is a 1, then you get a bunch of 1s. If that last one is a 0, well, you get a bunch of 0s. Now, registers can certainly hold full 64-bit values, but when you treat them as an address, only the low 48 bits actually end up mattering. It's fascinating, isn't it? So how does all this work? Well, conversion of a virtual address to a physical address is done through page table lookups. You may already know all this stuff, so apologies if you already know this and this is boring to you, but it's worth a quick discussion. Pages are 4,096 bytes long, 4K. That's usually true everywhere. That's what you should tend to assume. There are other page sizes you can use, but let's just assume for now everything is 4K. That means 12 bits, right? 2 to the 12th is 4K. 2 to the 10th is 1024. 2048, 4096, so that's 2 to the 12th. So the bottom 12 bits of the 48-bit address are the offset into a particular page, which means those other bits from bit 12 up to bit 47, those must somehow select a page. And here's how they do that. The 36 bits in that top, right, 48 minus 12 is 36, are divided into 4 groups of 9 bits each. Each group corresponds to one level of the page tables. So the highest ones are the level 1 page index, and the level 2, level 3, and level 4. Levels? Yes. Why 9 bits? Well, a page is 4096 bytes. A full pointer is 8 bytes. So a single page can hold 512 pointers. So think of this for a minute. I've got a page, it's 4K, and I'm going to have that page hold pointers, other 64-bit addresses. Each of those is 8 bytes, so I divide 4096 by 8. 4096 divided by 4 is 1024, then divide that by 2 and it's 512. So 512 happens to be 2 to the 9th, so each of those will be 9 bits. What? This will make more sense once we see how it all comes together. The top 16 bits, though, aren't used, and the bottom 12 bits are given by an offset, so why aren't we just using 36 bits in there? Well, it's because we need extra bits for each address for flags and other stuff. Alright, what do I mean by that? Whew. So an address stored in the page table really only needs those 36 bits. Okay, what else is in there? Well, it's other stuff, right? Here is the format for an entry in the page table, and you can see there's a lot of stuff going on there. You might have 28 bits, 40 minus 12 is 28. You might have 36 bits, which we've been talking about, 48 minus 12, with the bottom 12 bits all 0, so the address is aligned to a page boundary. The address can grow to 59, because the top bits are used. But, you know, this is a little bit wild. You can have other page sizes than 4K. On the Intel 64-bit architecture, you can have 4K, 2 meg, or a gigabyte. And you can mix those if your operating system supports it. Jumbo pages. So, let's go back to page tables. And let's see how we get from a virtual address to a physical address. Well, the register CR3 holds the physical address of the level 1 page table. That's how we get the whole thing started. And with the GOT, we needed to have at least one real address. Same thing here. I need to have at least one real address to tell me where to look. Once I have that, I'll have an offset in the level 1 page table. That will give me a new address, which I can then carry forward. You can get the contents of that register, but only if you're within the kernel. If you try it from user space, you'll get an exception. And you should try it. Write some code to access register CR3 and see what happens. Nothing's going to blow up or kill you. It's just going to cause an exception. So let's see this at work. So CR3 points to a page. And again, addresses are going up as you go up the slide, so the lowest addresses are at the bottom. CR3 points there. The page is 4K in length, and that is the level 1 page table. It's 4K long. That means it can hold 512 addresses. 512 full 64-bit addresses are really 512 36-bit addresses with other bits that specify control information. So there we go, a point there. Once we have that page, we use the level 1 page index to go and select one of those 512 addresses from that page. And that points to another page table, a level 2 page table. I said a level 2 page table, right? There can be 512 different level 2 page tables. And this points to one of them. Now, we use the level 2 page index to go and get another address, and that will point us to a level 3 page table. Okay, and you can see what's happening here, right? If there were 512 possible level 2 page tables, there are 512 squared possible level 3 page tables. And that makes sense, right? 9 bits specifying an offset into there, 18 bits specifying a level 2, and then 27 bits specifying a level 3. Again, we use an offset into the level 3 page table to go get an address. That points to a level 4 page table. We use an offset into that, and that one points to a page. A real physical page somewhere in real physical memory. I have the real address of the piece of physical memory. And in the last 12 bits, specify an offset somewhere into there. And that's how we get from a 64-bit thing into an actual location in physical memory. Okay, this may seem complicated, but consider what happens when you cross page boundaries. Let's say I want to load an 8-byte thing out of memory, and those 8 bytes cross a page boundary. How does that get handled? Because I might now have to do a different lookup for a different address, maybe. Right, if those bottom 12 bits are close to all ones, and I reach out, I'm going to have to do a different level 4 page lookup, or maybe even a different level 3 or level 2 page lookup. It can get complicated. That's why we don't like that. We like things to be aligned in memory, right? If I align my keywords on 8-byte boundaries, that will never happen. So that's what we like. This all seems like it's going to take a while. It's going to take time. I have to go get a page that's probably in cache. Get another page that's probably in cache. Get another page that might not be in cache. I mean, this is getting messy. So I speed this up using a translation look-aside buffer, or a TLB. I cache the address and the virtual address and the physical address so that I can then quickly look them up later. Let's talk about Linux memory maps. You can go and see the memory map for a particular process using the info command from within GDB. So if you start a process or you start up GDB with it, you can go and take a look at what's in the memory map. It's going to show you all the symbols and the start address and the end address for each of those little areas. So for example, we can see over here on the right, the PLT occupies hex 4020 to hex 46C0. The GOT is down here at 23C58, and it runs to 23FF0. These are not final addresses because we haven't actually set things up in memory. So here, we do an info file, and we can use this to see them after we've started the program with start I. So we come in, you do a start I, then you do info file, and now you'll see information like this. Using the running image of a child process, there's the PID, and here we see all of the information here, and now we have full memory addresses. Those 5 show up because we've loaded it into memory. And so we actually see the runtime addresses. What's really in an address space? So let's go back for just a moment. Remember that when we did this, it told us the PID of the process, 55822. We can also get that with info proc. Once we have that, we can go to the proc file system and we can go look at the process memory by saying cat/proc, the PID, and mem. And that will let us take a look at the process's memory map in a little bit different way. So instead of showing us all those little sections and how they got mapped, we'll see the different memory chunks that have been allocated. We'll see their permissions as well. So over there, when we do that, we see the start address at the beginning, the end address, and those are virtual addresses. If we just highlight those, you'll see that they occupy some small chunk, but you'll notice that all the last digits are zeros, right? We are the last 3 digits are all zeros. 3 hex digits. What is that? Well, each hex digit is 4 bits. 3 of them would be 12 bits. So, those are those bottom 12 bits, and they're 0 because we are allocating full pages. Over here are the permissions. Read, write, execute, and then pages can be private or shared, right? Most of them are going to be private. Something like a shared library that you're sharing among many different processes might then be shared. Here's the offset into the file if the thing we're talking about comes from a file. And for those first ones, you see they come from user bin ls, and so they actually do have a relevant file offset. Heap, however, does not. This is the major and minor device number if it's from a file in hexadecimal. What in the heck is that? So major device numbers indicate a device driver in the kernel. Okay, for example, flash drivers, for SSDs, drivers for like IDE hard drives, all those things have an associated number. You can go look at proc devices and at /dev to go in and take a look at those. The minor device number selects a particular device or a view or maybe a partition, etc. Those two together point you to a structure somewhere that will contain the file. All you need then is an actual pointer into that to the file itself, which we'll have in just a moment. So remember, 103 is the major number. That's in hex. We can convert it to decimal using the trick you see there: echo $, open 0x103 close 259. So if we then list in dev and we grep out 259, we'll see that 259 refers to some of the NVMe drives on my system. And in particular, the one that's bolded here, 259, and 2, which is the minor device number, refers to NVMe 0N1P2, this particular partition on the device. So there we go. After that, we have a file number. What is that? That's an inode number? You can see file inode numbers with ls-i, and you can actually search for inode numbers with -inum in find. And so that combination, 103, 02, and the number, actually tells us this file, and proc has been good enough to do all that work for us and then show us the actual path to the file. But this actually specifies it unambiguously. So here I use debug fs. Fs is file system, debug file system, and I use -r, incheck, and the file number, and I know what the partition it's on, and that will then point me to the specific file for that inode, and you can see, sure enough, it's user bin ls. At the end there, we have information about what it is. In some cases, it's a file. In the other case, as you can see, it's like the heap. We should be able to figure out something about each of these chunks. For example, this one memory chunk is executable. That's probably where the text section is. This one is not executable, but it is readable. Very likely where .data is located. Readable and writable? Very likely where BSS is found. There's the heap. It's readable and writable, but not executable. The program break is the lowest address outside the program space, and it marks the end of the heap. So the heap runs from this first address to 578,000. That address is the first non-allocated address, and it's called the program break. The program break is managed by the operating system, and you can change it with the break system call, and you give it a new address, and it moves it to that address. If you give it 0 as the new address, it will give you back the current program break. So, let's take a look at how that actually works. So there's the break system call. We give it the new address or 0 in RDI, and we invoke number 12. So we put 12 in RAX, put an address of 0 in RDI, do a syscall, and we get the result back in RAX. Let's take a look at how break actually works. So I've got a little program here, break.asm, and this will be available online. And there's different stuff we can try out. I give you some examples at the start of things you might want to try. But let's go see what we're actually doing here. So here we start out, usual preamble stuff. We go ahead and get the program break and print it. How do we do that? Well, we move sysbreak into EAX. What is that? That is a macro. Sysbreak is defined to be 12. And if you'll recall, 12 is the number for the break system call. So down here we put 12 into EAX. I zero out EDI because I want to know what the break is, and I do a syscall. Then I save RAX, and I do some stuff here. Basically, I print it out. This lets me print out the result. So I save RAX, I put RAX into RDI, print hex, print a new line. Now, I actually want to change the system break to allocate an additional page. So I again put sysbreak into EAX 12. I move RSP address, the address that's stored at the address pointing to my RSP into RDI. What's happening here? Well, I pushed RAX up here. So what's stored, right? Remember, RSP points to the last thing pushed. So in this case, it points to the value that was in RAX that got stored. Namely, it points to the stored system break value. I put that in RDI, and then I add a page to it. Page is defined up at the top, be 4096. So I add 4096 to it. I do a syscall to give me back the system break, but now with a new page. I go ahead and print out what it returns. I then come down here and I again put 12 in EAX. I pop RDI, so now I'm actually taking the address off the stack because I don't need to keep it saved anymore after this, and putting it in RDI, and then I want to allocate 32,000 additional pages. And then I do a syscall. So now I've allocated a bunch of memory. I move REX to RDI. I print it out. I then move sysexit group to EX, 0 into EDI, do a syscall and halt. So there you go. The rest of this deals with printing. So I'm going to go and show you the system break. I'm going to allocate an additional page. Right? Then I'm going to allocate a bunch of additional pages, and then I'm going to exit. So let's go ahead and build it, and you'll notice I'm building it as a dynamically linked program. Sure enough, that's what it is. Let's go ahead and run it, and let's see what happens. Here's the initial program break, ends at C1000. Now I'm going to add an additional page to it. Remember, these bottom three are the 12 bits that specify an offset into the page. So this is the first thing that's actually specifying a page. Adding a page should increase that by 1, and it does. We go from C to D. Now I add a bunch of them. I add 32,000 additional ones. So that should, where is that going to be, right? That's not going to be here. This is a 12. That's 16. That is going to be 20, 24, 28. So we should be right here, right in this space. And sure enough, look at that. This goes up by 1. EA, I'll do this in my head. Should be 8, right? Should go up by 8. So this is this is too hard for me to think about. 8. So A, B, C, D, E, F, 0, 1, 2. Yes, that's right. So it should be F2, and it is. There we go. So, yep, that all worked just fine. A little bit tricky to think about. Back to the memory map. Here's some more from our memory map. We have, you see here's the initial stuff, but then we have these higher addresses, and they hold VVAR and VDSO. What are those? VDSO is a library exported by the kernel. It contains some system calls that don't have to run in kernel space. Getting the time of day, certain things, you don't want to have to do a context switch to the kernel every time you do that system call, and this provides you with a way to not have to do that. You need some additional data. That data is mapped into VVAR. So VDSO has those kernel calls. VVAR has the data that they need. Some more stuff. Look at that. LD Linux x86-64 SO2. What is that? That's the dynamic loader. It's a program just like LS is, and so we should expect its little memory map to look like LS's, and it does, right? There's its initial information, its tables and headers and so forth. There's its text section. There's probably its data. There's its BSS. There it is. We might also see shared libraries mapped into this space. There's our friend the stack. Again, high memory working its way down. and you can see we have space allocated for the stack, right? It's going to be up here all the way down to here. That's the space we have allocated. What if we need more space for it? We'll have to allocate more space for it. The default size for a thread stack is 8 megabytes. Now, if you are using Rust, your process may have a smaller stack. Each thread may have a smaller stack. But 8 megabytes is the default size for a thread stack. Here is the older vsyscall interface. Now, what happened to the addresses? We went from this to this, right? What happened was this 7, remember that's the bottom 3 bits of a nibble. I go up one more and it's 8, and that high bit is set. Bit 47 is set, and it copies all the way across the other bits, and I wind up with this. So it's this guy right here. The next page up above this is going to immediately have all these Fs set. vsyscall is an older fast system call interface like VDSO, just an older one that's hanging around. Other processes may look a little different. Here is an instance of Python 3.9 running, and we took a look at it. It's got a heap. It's got some shared libraries mapped into that space, and they all sort of look the same, right? There you go. It's got some other stuff in the space. Here's the standard C library. libz is a compression library. Here's its own copy of the loader. There's its stack, vvar, VDSO, and vsyscall, all happily together in high memory. Whew. So you can allocate space by moving the program break. When you move the program break, the kernel will try to take care of that for you. It will say, oh, you've moved the program break. I need to go and see about allocating some additional pages so that I can make this new program break work. Another way to do this is with mmap. So this is how most memory management is actually done. In fact, if you go and dig around in the program break stuff, it has to map memory as well, and it's going to need to use basically the same mechanisms as mmap. So mmap is not like the program break. Program break is super simple. Here's an address, here's a new address. Good to go. Mmap, as you can tell from this example, has a lot more moving pieces. So it's syscall number 9. You need to provide it with a address where you want the memory, a length, how you want it protected, okay, flags associated with it, a file descriptor in case you want to actually map a file into memory, okay, and so we'll see all of that. The first thing is the preferred address, or it can be 0. If it's 0, the kernel gets to decide what the address is for you, and that's usually what you want. The length is given, protection modes, flags, a file descriptor, if that makes sense, right? You're going to have part of a file mapped into memory. We know what the length is because that's given. Where do I start mapping the file in? Well, that's given by the offset. This is the offset, 0-based offset into the file, where I would begin mapping it into memory. Let's see an example of that. So here we are in mmap.asm. I declare a bunch of constants. In particular, you'll notice mmap, which is 9, right here, is also an munmap, which is 11. And then I define a bunch of other usual stuff like how long a page is. I define some flags that I'm going to use later on. And I point out where these come from. These come from this can be found in this particular header file. All right, let's take a look at what we're actually doing. Usual boilerplate here. Then I want to grab a page of memory and make it writable. So I put mmap 9 into EAX. I let the OS choose where to put it, so I put an address of 0 in RDI. I want 4096 bytes, so I put the page size in RSI. I want the page to be readable and writable, so I OR those two values together and put them in RDX. I want it to be mapped anonymously and privately, so I OR those two together and put them in R10. I don't have a file descriptor associated with it, so I'll put -1 into R8. And I don't have a file offset, so I probably could ignore R9, but I go ahead and put 0 in there just to be complete. I do a syscall, and that should give me back a page somewhere in memory with the address in RAX. So again, I put this here to save it. This is putting it in this scratch area on the stack. I reserved 16 bytes up here, and so I'm putting it there to store it. I go ahead and put it in RDI and do a print hex and new line, so I print it out. Now I want to grab a chunk of memory. Same as I did before, I want to grab 32,000 pages. So again, 9 goes into EAX, 0 into RDI, let the dealer choose. The size I want is page times 32,768. And I want the best kind of memory. I want readable, writable, executable memory. That's the best kind, right? This explicitly violates the security principle we've talked about before, which is write, exclusive or execute, right? W:(x). I'm violating that principle. Love it. I also want it mapped anonymously and privately. I don't have an associated file, so there's no offset. I do a syscall, and again I get this back and print it out. Now, I want to try something a little bit different. So this isn't going to work. The reason it's not going to work has to do with this line right here. So I'm going to go ahead and tell it once again 9, 0, page, read write, map anonymous, but not map private. Okay, so this is going to basically tell it I want some memory, but I'm not going to specify that it should be private. It's not going to work, and so I'll do a syscall and nothing will change, and I should get an error. I won't see the error, I just won't see anything change. At this point I have a couple chunks allocated, so I'm going to use munmap to remove them. So here's the big one. I'm going to copy it in here. I'm going to copy in the amount to deallocate, and I'm going to do a syscall. This is only going to deallocate part of it, right? I allocated 32,768. I'm only deallocating 16,384. So about half of that should go away. Then I'm going to unmap that little single page that I allocated, the full page, so it should go away altogether. And then I'm going to unmap the rest of that memory. So I unmapped the first 16,000 pages, and so now I add 16,000 to it to get the correct address, and I deallocate the remaining 16,000 pages, and then I exit. So let's see how that works. Let's go ahead and control, I guess, sure, I don't think I made any changes. Make mmap.asm. Great, and now let's run it. And I get some information out. Remember, first I'm going to allocate a page, then I'm going to allocate 32,000 pages, and again we have to count over 1, 2, 3, 4, 5, 6, 7, 6 and 7, so it should be here. It's 32,000 pages, so again, let's think about that. So that should be, This is a little more, but that's okay because the address doesn't have to be the same. This is the start address of where it allocated those pages. And then, of course, for this one, it fails, so I don't get back anything. There we go. Let's think about memory management using the standard library. So we can use the C runtime and the standard library to manage memory for us. Library functions are declared in standard lib.h. They're available in libc.so, and they are malloc, calloc, realloc, and free. And you can use them in your assembly like any other function, right? You extern them, and then in this case, I use the calling convention. So malloc takes a single argument, which is the amount of stuff I want. 64 times 1024 in this case, right? 64K. I put that in EDI, and then I call malloc with respect to the PLT. The newly allocated memory comes back to me pointed to by RAX. When I want to free it, I put that in RDI, and then I just call free with respect to the PLT. There you go. There you go. There are lots of alternatives to this. You can build your own malloc. You can find other people's mallocs. You can straight up use mmap. It's up to you. Let's take a look at an example of using malloc. So here we are in yet another little program. This one's pretty simple. Usual stuff. I'm going to print out the program break, and then I'm going to allocate a page using malloc. And I'll print out the program break again. Then I'll allocate 32,000 pages, and I'll print out the program break again. And then I will call free to deallocate the space. And that's it. And there we go. I allocate a page, and so I get this value. I allocate a bunch of pages, and so I jump up quite a bit. I then deallocate some stuff. I can't remember the exact structure of it now. Let's take a quick look. What am I doing here? Yeah, so allocate a page, print, grab an additional two pages, or additional 32,000 pages, and print it out. So initial break after allocating a page, break after allocating 32,000 pages. Sorry about that. So initial program break, allocate a page, and you'll notice I don't get just +1. I get a different value here, probably because it's not practical to just allocate a single page. It's more reasonable for the malloc system to allocate a bunch of pages because it has its own business to take care of. It has to do its own memory management. It has its own tables, etc. It basically builds a linked list of the different chunks I allocate. So malloc has some overhead associated with it. And then finally, when I allocate the giant chunk, the program break doesn't change because it doesn't move the program break. It uses mmap for that big chunk. So it's free to choose whichever approach it wants to use. There's homework. Let's do next time. And what I want you to do is write position-independent code. Takes a single argument, which is the file name. Open the file, get the size. There's a function you'll need to do that. Allocate space to hold the content of the file and read it into memory. Write out the content of the file in reverse to standard output. If anything is wrong, write out a message starting with the word error and exit with an exit value of 1. If there are no errors, exit with an exit value of 0. Name program reverse.asm. There's how I'm going to build it. And if you want to use Makeline to build it, there's a Makeline for you. An example would be the following. So I've got test1.text. It says, hello assembly world. I do my reverse test1.text and it writes out, hello assembly world, backwards. I will test your code with some files. It'll all be 7-bit clean ASCII. Just reverse the bytes. Be sure you can handle an empty file, a missing file, an unreadable file, and handle running out of memory. How can you force yourself to run out of memory? This will do it. So systemd run scope -p memory max 800k --user reverse. This will run reverse, but it will run it with a lot less memory. Here's a template to get you started, and that's it.